Hello and welcome to this video on radioactive decay and nuclear radiation. So just to show you on the specification here, just before we get started, there's some key info that we need to understand. So what we're looking at is we're looking at the idea of radioactive decay. Now, the reason this happens is that some atomic nuclei are unstable, as it says here. And because of this, the nucleus gives out radiation as it changes to become more stable. So the idea is to gain further stability. And this is actually a random process. Okay, we can't predict it. It's a random process, and that process is called radioactive decay. So there's three types of radiation that we're going to go into in just a moment, but from definitions just to get us started. So just looking here, the activity is the rate at which a source of unstable nuclei decays, and that activity is actually measured in what's known as becquerels, and the unit for that is BQ. So the more active an unstable nuclei is decaying, then the rate would then be higher. The rate would increase. Now, just to pop down here slightly, when we're looking at the count rate, we can detect the count rate using something called a Geiger-Müller tube. And the Geiger-Müller tube basically counts, as it says here, the count rate is the number of decays recorded each second. So every second, the detector detects how many radioactive decays are present, and that is then the count rate. And just to further emphasise once more, the radioactive decay is a completely random process and it cannot be predicted. Okay. So there are three types of radioactive decay as seen from this image here. We have alpha, we have beta, and we have gamma. I'm just going to go over those in a little bit more detail just so you can understand that. So when we're looking at alpha, which is this image that we see here, what you've actually got is you've got a helium nuclei. Okay, and you may remember this from previous videos, but what that basically is two protons and two neutrons without the electrons around the outside. Okay, so the alpha particles that are positive, that is what they are. Okay, there are two protons and two neutrons, and that has an impact on the mass number when that radioactive decay occurs. We'll go through that in a little bit more detail in just a moment. You also have beta decay. Okay, so this one here is alpha. This one here is beta decay. And what happens with beta decay is within the nucleus you have a neutron, but that neutron changes into a proton, and when it does that, it also emits a high energy electron as well. Okay, so a neutron that changes itself into a proton and then emits a high energy electron out of that nucleus. Okay, so the electron does not come from the electrons in the electron shells. Now that also has an impact not on the mass number, but it has an impact on the atomic number, and again we're going to look at that in a little bit more detail in just a moment. Now when we have our gamma, so these two that we've just spoke about, we spoke about alpha and we spoke about beta, and they involve particles. Okay, gamma does not. Gamma is energy, and it is an energy ray as part of the EM spectrum, and that is what is emitted after alpha and beta decay occurs. Okay, so that is our gamma radiation. So that has no impact on the mass number, atomic number, etc. So just to give you an example here of alpha decay. Now we're going to go over this in a later video in more detail when we're talking about nuclear equations, but just to give you a bit of further info. So we've got our radioactive nucleus here. This is a uranium nucleus, and what's happening is alpha decay is occurring. Now you can see this because the alpha particle, the radiation that's being emitted, is an alpha particle here. Two protons and two neutrons. Now, what happens because the nucleus is losing two protons and two neutrons? That has an impact on the overall mass number and atomic number of that unstable nuclei. So here, where we've got 238 uranium 92 atomic number, because alpha decay has occurred, which is what we're seeing here. Okay. What we actually do is we have to take 4 from the mass number and 2 from the bottom number. Now the reason for that is, and it actually then changes the element, the reason for that is that we end up changing from uranium to thorium. And what we end up having is 2 234 as our mass number and 90 as our atomic number. And what's left over is 42 that has come out. Okay, a helium nuclei has been removed. Now, the reason the element changes, the element itself changes, is because, as you will remember from previous videos, the atomic number defines what the element is. So where here we had 92 protons, because through the alpha particle being emitted, we've lost 2 more protons, that actually changes the atomic number and therefore changes the element that we are discussing. So we've gone from uranium to thorium, as that thorium has 90 protons. Now, the reason the mass number, the top number, has changed is because overall our alpha particle is 4. And if you remember, again, from previous videos, the alpha particle, our nucleus, is our mass number, and the alpha particle consists of protons and neutrons. So if we've got 2 protons and 2 neutrons, that means our mass number is going to go down by 4 in total. So that's why we've gone from 238 to 234. And we just symbolise that by showing that a helium nuclei and an alpha particle has been emitted from the nucleus. So that's an example of alpha decay. We're going to go over that in a later video in more detail. Then when we look at beta decay, now remember what I said just a moment ago. So if I just scroll back up, when we're talking about beta, we are talking about a neutron in the nucleus changing from a neutron to a proton, and whilst that happens, a high energy electron is emitted, which is known as the beta particle. So what actually happens in this beta decay example? Very clearly, we start with lithium, okay? And this is an isotope of lithium, but nonetheless it's lithium because it's got 3 here on our atomic number. Now, as we've said already, a neutron changes to a proton and emits a high energy electron, a beta particle. Now, the impact that has on the atomic number and the mass number we're now going to look at. Now, the mass number, you'll notice from here to here hasn't changed. So when a neutron changes to a proton, it doesn't have an impact on the mass number. You're swapping 1 for 1 because they're both in the nucleus. So if you're changing from 1 neutron and it's switching itself to becoming a proton, the mass number won't change. It's just an extra proton in the place of that neutron. But if you are changing a neutron to a proton, which is what is happening here in beta decay, the atomic number will change because the atomic number, you'll remember, is our proton number. So when we have a neutron changing to a proton, we're actually changing from 3 protons to 4 protons. Our atomic number goes up by 1. Now again, just to make it clear, the proton number, the atomic number, defines what the element is. So if there are 3 protons, it's lithium. If there are 4 protons, it is beryllium. So when beta decay occurs, the element will actually change. The proton number, the atomic number will go up by 1 and therefore affect what the element is. So we're going to go over that in more detail in a later video, but that there is a brief insight into nuclear equations and what happens when alpha decay or beta decay occurs. With gamma, there is no change to the mass or atomic number. That is just energy that is being released. Now, just to scroll down to give you a bit more further info once again. So you do need to understand about penetrating powers and ionization and ionizing powers of the 3. So we've got alpha decay. Now, in terms of we'll talk about penetrating first. So in terms of alpha decay, alpha is least penetrating. So alpha decay can be blocked by a few millimeters of air or just a thin sheet of A4 paper or any paper to that matter. So an alpha decay can be blocked by a few millimeters of air or a sheet of paper. Then we go down a little bit further, and beta is slightly more penetrating. So beta decay actually can go through paper and a few centimeters of air, but it will be blocked by a thin sheet of aluminium. So a thin sheet of aluminium, which is like what your Coke cans are made out of, that will block beta decay. Okay, and then going down to what is the most penetrating. So looking here just at gamma, gamma is actually able to penetrate through paper, through aluminium, And depending on how much energy the gamma ray has, will either be able to penetrate through, if it will need to be blocked by a few centimeters of lead or a few meters of concrete. So gamma, highly, highly penetrating. Now on the flip side of that, we're talking about ionizing. Now what ionizing means is just the ability to change a particle or change a molecule into an ion. Okay, so, and this can be quite dangerous for us as living beings. So alpha is the most ionizing. Okay, so going up this arrow here, alpha is the most ionizing. So alpha can be quite dangerous if ingested inside us, but will actually be blocked by gloves or anything on the surface of our skin. Whereas beta is slightly less ionizing, and gamma is the least ionizing. So the most penetrating, but least ionizing. And just to finish off, just to make that very clear, because you do need to, based on the specification that I showed you above, need to be aware of the range of these types of radiation in air. As I said just a moment ago, alpha, the range in air is just a few millimeters. That's all. And again, can be blocked by a thin sheet of paper. Beta is a few centimeters. And as mentioned previously, can be blocked by a sheet of aluminium. And gamma is actually infinite. So gamma rays can just go on and on and on. They can travel through a vacuum. They are part of the EM spectrum as mentioned previously. So they are your ranges in air. If you've got any questions, please pop them in the comments below. Good luck and keep studying. Well done.